Hey, welcome back to another video. So I'm come to a point where I have a lot of artwork I want to simulate in the VIC2 dieshots that I'm vectorizing, and I found this cool project which has a simulator for Z80. But first let's have a look at Visual 6502. The problem I have is going from this to a transdef file. That's a list or a net list by transistor and all the connection in between. So I'm sure you have seen this project before. It's the Visual 6502. I have reached out for some of the guys and asked, like, how do you go from dieshot to transdef file? And if you go to Visual 6502 on GitHub, you will find the file, and you see it's just a list of numbers, right? But then I found also a subfolder here for another chip. It also has a transdef file. It's a name, so it's transistor 1, and then you have gate. So I believe these numbers are unique for each connection or net. So you can see all these 4 transistors or 5, they have the same gate. And the next one is the left and the right side of the gate, or source or drain, doesn't matter. You can see also some of these transistors are connected in series, like here. So because if it's the same number, it's the same net. So, and a lot of these have the same numbers. I think maybe it's a power or something distributed over many transistors. So I found this other project which here for Hoglet, a Z80Simulator. Now the Z80Simulator, it's a bit different. It's written in C++. It goes by dieshots only, or artwork from it, in a way cleaned up. And then when the poly crosses the active area, you get a transistor, so it registers that. And also it routes, so it puts all the layers in a stack, and then it can route the signals. So then you get signals, so first connections, then signals, then transistors, I think. Not sure yet. So you can see here, you can see how clean they are. I think I can view this one. So yeah, Z80 metal, yeah, and so on. So let's grab this project and let's try compile it. Let's have a look. So I'll go into my test folder. I will clone this project. Also you need now it's cloned. Also you need PNG. I have installed that, so just write in Ubuntu anyway, libpng --dev, but I'm not going to do that right now. So, and then I go into that. So let's have a look. You can see the readme. So you need to build it. Just run that one. So it's already built. You probably need some development tools like build. Okay, let's see. Now we have got a file there, Z80Simulator. Z80Simulator. Need a file. What file do we need? Okay. So I'll just put Z80 and it will find the other files. So let's try that. So I'm probably going through all the... Yeah, now it started simulating. So take about 8 seconds, I think, for it to find all the transistors in the file. One thing you can do in Linux is write strace. You can see what it does. So let's see. There you go. Z80 pads, Z80 polysilicon, and so on. So let's look at the source code. There's only one source code here, so I've looked at this before actually. So yeah, anyway, we can search for main. And here are all the arguments, so you can add verbose. Let's try that. So verbose. Look. Now it will start spamming though, so alright, so we see the metal is 53%, Z80V has 2.3, 3.3, now the final goes on. Let's stop the simulation. And after all this here, we get transistor count 8880. So if we go back to Firefox here, we can look at Z80 on Wikipedia. 8,500. It's a bit off. Don't know why. So maybe, but I think they are just, you can see it's, on Wikipedia it's rounded up to nearest 500, it seems. So should have been rounded to 9,000 then. Or yeah. So yes, it counts up everything. You can also, if you change the source code, you can also print out all the transistors I saw yesterday. It seems to be the hard-coded part here is all the layers and all the pads. We'll see that in the main at the bottom. It has a large buffer to stack, and you have to supply memory and ports for it to simulate. So the first class you get is connections, basically just terminal, and you get an index, and this is for a simulation, doesn't matter. And the next signal class is signal, which uses that other class. So it's just a list of connections. And homogenize, that's to share, or like if they're connected together, they have to have the same value, so it just moves charge around, I think. That's what it means. Okay, it says up here also. Okay, then it sets up a signals variable. Then you have pads. They are also a list of connections. And finally you have transistors. And finally I'm just going to show you the pads. So now we are main. This is where the program starts, sets up memory. This is the program it's going to run, by the way. So it just runs for, so this is 16, 17 instructions. Here it sets up all the pads. There you can see how it's hard-coded. I was thinking maybe automating this somehow, like it can find it itself. Maybe that's a bit difficult, unnecessary also. So if I'm going to simulate my own work, I was thinking just taking a small part like a counter and putting some pads around it. Yeah, and then applying signals on the inputs. So yeah, that sounds, maybe it actually looks like a lot of work anyway. Here you can see, here you can print out all the transistors, and when you simulate you can then see registers. So you see register PCH, R, I don't know the Z80 very well, but they are hard-coded, so just find the transistor by location. So let's simulate it, see what happens. Sorry for this, I need to make the screen a bit smaller. So first goes through the layers, does some statistics. There, the simulation starts. So what you can see is this is maybe a bit too big. Yeah, it's too big. You can see over here you see 2, 3, 4, 1, 2, 3, 4, and so on. I think these are like fetch and execute phases. So it reads memory, fetches opcode, memory write. You can see the program counter is now at 8 hex, 9 hex, A, E. I'm not sure if you can see the instruction, but it's really cool that I actually can do this. Like simulate a whole processor from just die shots. There's a lot of hardcode stuff in here, but you need that to like tell the thing where all the registers are. So that took 91 seconds, and we run at 1.34 hertz. So, yeah, it's pretty cool. So you can use that for verification of other designs, like FPGA implementations. Of course, you can maybe derive all the logics out of this somehow in the future, if you know how to do that from dieshots. But I don't know how to do that. It's another thing that is really hard, so hope you found that interesting. So thank you very much for watching. And yeah, it's been like 3 weeks, like the last dieshot video, but I'm still working on it. Almost finished with all the vias actually, 100%. So that's really cool. That's why I'm thinking about doing stuff like this.